Okay. Hello. This is Alexander Medlyn. Today, I guess we're going to be continuing whatever whatever you call this. I'm not really just trigonometry, trigonometrical equations. So our first example. Oh shoot. Our first example is going to be solve cotangent x times cosine squared x. We want to find where that equals 2 cotangent x. Okay. So the first thing we're going to do is we're going to subtract the cotangent x to the other side. So we're going to get we're going to get all that equals 0 just by subtracting the 2 cotangent x from one side to the other. And then what we're going to do next is we're going to factor out a cotangent x. So it's going to look like this. Okay, so just like that. And then now, just like a typical factoring equation, we want to find where each piece equals 0. So we want to find where cotangent x equals 0 and where cosine squared x minus 2 equals 0. So the first one's going to be cotangent x. It's a pretty bad arrow, but so we're solving for both of those. And I guess what we're going to do from there is we'll start with this side um, where cosine squared, we add the 2 over, and then we just get cosine squared x equals 2, which we know is not possible because cosine does not exceed 1. Um, so even if you take the square root, you just get cos x equals the square root of 2, which is greater than 1, which isn't possible because the maximum value of cosine is 1. So that part is just going to end there. And then this part we solve for where cotangent x equals 0. Which is at, if you think about the unit circle, hold on, think about it too. It's pi over 2. So at pi over 2, cotangent x equals 0. But think about it. Okay, and then so that's our particular solution is at pi over 2. But we also need to make a general solution. So we say x equals pi over 2. Oh, let me erase that. Looks terrible. You say x equals pi over 2 plus this value k, and we need to multiply that by the period. And since the period of cotangent x is pi, it's just going to be pi over 2 plus pi k. Okay, so that is our final answer for that one. So hopefully that made sense. And we'll just dive right into the next example, which is going to be 2 sine squared x minus sine x minus 1 equals 0. So this one, for this one, we want it only on the interval from 0 to 2 pi. So I think Ms. Williams said this is the first time you guys are dealing with like restrictions. But basically all that means is we're not looking for the solution with like the pi k or 2 pi k. We're only looking for the solutions in the first period. So that makes it a little bit easier for us. So looking at this problem, all it really is just factoring. So it ends up breaking down into two pieces. The first is 2 sine x plus 1. And the second one is just sine x minus 1. And then if you were to FOIL that all out, you would end up getting the above term. So 2 sine squared x minus sine x minus 1. And then so we do the same thing we did last time. We're just going to set each of the pieces equal to 0 because like this equals 0. So the first thing we're going to do is where 2 sine x plus 1 equals 0. And the second one we're going to do is sine x minus 1 equals 0. So this one's going to be easier because it's just sine, where does sine x equal 1 on 0 to 2 pi, which is just pi over 2. And this one, you have to do a little bit more. The first thing you want to do is subtract the 1 over. So you're going to get 2 sine x equals negative 1. So sine x equals negative 1/2. That's just by dividing the 2 over. Okay, so now you think, where does sine x equal negative 1/2? And it's actually in 2 places, because if you think about the unit circle, there are 2 instances where the y coordinate is going to be negative 1/2. The first is going to be at 7 pi over 6, so just after pi, or 180. So 7 pi over 6 is the first one. And the second one is going to be right before 2 pi. It's going to be 11 pi over 6. So both of them pretty close to a value of pi, but they're still contained within our interval 0 to 2 pi. And then all we have to do is just check to make sure all of these are in the interval from 0 to 2 pi. And that's this interval right up here. So we just have to make sure they're in that range. And all of these ones are, because they're all going to end up being less than 2 pi. So our final solutions are x equals pi over 2, 7 pi over 6, and 11 pi over 6. Yep. And that's that example. I'll scroll through it one more time with the whole thing. Okay. We'll just jump right into our next example. Let me get my notes right. Okay. The next example is 2 sine squared x plus 3 cos x minus 3 equals 0. Okay, so this one is going to be a little bit of a longer one. The first thing we're going to want to do is put it all in terms of one variable. So in this case, we're going to pick cosine. And what we're going to do is we're going to use the identity. You guys remember that sine squared x just equals 1 minus cosine squared x. So that's the first thing we're going to do, is break it into that. So it's going to be 2 times 1 minus cosine squared x plus 3 cosine x minus 3 equals 0. What we're going to do after that is just factor out this part of it. So we're going to get 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. And then we can combine the positive 2 and the negative 3. So then we're just going to get negative 2 cosine. Actually, why don't we start by no, we'll just keep going with this. So we're going to get negative 2 cosine squared x plus 3 cosine x minus 1 equals 0. But it'll be really nice if we can have our leading term be positive. So this one. So we're going to add this over to this side, add this over to this side, and subtract this. So it's going to end up being positive 2 cosine x. My 2's look terrible. Cosine squared x minus 3 cosine x plus 1 is what we're going to end with. And then, just like the one above, this one is just factoring as well. So we break it into 2 pieces. The first one is going to be 2 cosine x. And this is just factoring just like you did in like algebra 2 and geometry and pre-cal. Factoring stays with you for a long time. So I recommend touching up on that if you haven't. And then the second piece is just going to be, oh wow, okay. The second piece is going to be cosine x minus 1. So as usual, we will start with the easier piece, which is where does cosine x equal 1? Oh, wait, we said this all equals 0. Oh, wait. So, yeah, we want to find where these pieces equal 0. The first one's easier. Cosine x equals 1. And we know that occurs just at 0. And then the second piece is going to be a little bit harder. It's going to be 2 cosine x equals 1. So where does cosine x equal 1/2? Is what we're looking for on this one. And thinking of the unit circle, where's cosine positive? It's going to be, or positive 1/2. It's going to be at pi over 3, because we're thinking where the x values are small. So it's going to be higher up with the y's. So it's going to be pi over 3 and a 5 pi over 3. X equals. But this one, we weren't given a restrictive domain to keep our answers in. So we're going to have to do the general solution thing where we have to continue adding whatever. So this function is dealing with cosine. We know the period of cosine is 2 pi. So we're going to have to add 2 pi k to all of these. So x is going to equal, we'll start with these ones here. X is going to equal pi over 3 plus 2 pi times k. And remember, k is just a constant. It could be anything. All we're saying is that that's going to be a solution no matter what value of k you put in. Our next one is going to be 5 pi over 3 plus 2 pi k. And our last one is just going to be 0 plus 2 pi k, because this is just 0. Let me just add that it's because the period is 2 pi. And I don't know if I made this clear, but basically all you're doing with this is you're finding the period of the function you're dealing with, which in this case is cosine, and then just multiplying it by some random constant k that you don't know, but all you're saying again is that it could be anything. So it doesn't matter what variable you even choose. It'll always work. So yeah, the last one, you're going to say 0 plus 2 pi k, which is just going to be 2 pi k. Okay. So those are the solutions for this one. I'll scroll through one more time. Oh, wait, is this too high? No, yeah, you're starting here. I'll scroll through one more time in case you wanted to catch up. But yeah. Okay. So our next example is going to be okay. This is going to be a bit of a longer one but there's reasons for that, and I'll get to that in a second. Basically, what we're going to say is cosine x plus 1 equals sine x. Now, this might look familiar to some of you guys, and that's because, actually, wait, no, I take that back. It's not an identity. But what we're going to do here is there's not much we can really do with this, right? We can't put sine in terms of cosine. So the only way to make it easier and cleaner is to square both sides. And if we square both sides, we have more terms to work with. But what we really want is to somehow get an identity out of this. And by squaring the cosine and the sine, we can get that because remember the identity sine squared x plus cos squared x equals 0 or equals 1. So that's going to be really useful. So we want to use that as much as possible. So we're going to square both sides. Anyways, so you square this piece and it becomes cosine, or this is just going to be sine squared x. And then the other side is going to be longer. It's going to be cosine squared x plus 2 cosine x. That's an x, sorry. Plus 1. Okay. So now we're going to do, like I said, is we're going to use our identity to change this. So it's going to be cosine squared x plus 2 cosine x plus 1 is going to equal 1 minus cosine squared x. And that's from the identity. Okay, so then where can we go from that? Well, we can start getting our like terms and trying to find a zero somewhere. And we're going to do that by subtracting this to the other side. So the ones are going to cancel out, right? This is going to be plus 1 minus 1. And then we're going to add the cosine squared to both sides. So we're going to get 2 cosine squared x plus 2 cosine x equals 0. Okay. From there, we are going to factor out a 2 cosine x to make life a little bit easier. So we factor out the 2 cosine x, and then that's just going to be, so if you take out a cosine x from here, or you take out 2 cosine x from this term, you're just left with cosine x. And then if you take it out from this term, you're just left with 1. So that is what we have, and we have that equals 0. So just like the other ones, what we're going to do is we're going to set each of these pieces equals 0. So we're going to say 2 cosine x equals 0, and cosine x plus 1 equals 0. Okay. So this side is going to be easier. It's just cosine x equals negative 1. Which occurs at x equals pi, because x is negative 1 there. So, or not negative pi, sorry, but just regular pi. And here, where does cosine x equals 0? Because if you divided the 2 over, it's still just 0. So then you're just saying, where does cosine x equal 0? Which is just at 0. Or not at 0, sorry, pi over 2. But you would think we're done there. We're not done there. So this is why this problem is a little trickier. Basically, when you square both sides, like we did right here, it's perfectly acceptable. But what's going to happen is you're going to get some solutions that don't actually work, because you square both sides. You're getting rid of some negatives and such. So you're going to, in most of the problems, you're going to get solutions that aren't actually solutions. But all you need to do is just plug them back into the original problem and see if they work. So we'll start with pi over 2. Actually, we'll start with pi. So cosine pi, just because remember our original problem was this one right here. Oh, wait, where is it? Oh, yeah, this cosine x plus 1 equals sine x. So we say cosine pi plus 1. Whoa. Cosine pi plus 1 equals sine pi. Now, what's cosine pi? It is just is 0. Cosine pi is 0. So we get 0 plus 1. Wait a second. Oh, yeah, no. It would be 0 plus 1 equals negative 1. Right? Oh, wait, hold on. Okay, I'm back. I got distracted, so I don't even know what I was talking about here. But we're just going to erase that. What was I saying? Oh, yeah, checking solutions. Okay, all you got to do with the checking solutions is just plug in the values you found here, which I also realized cosine x equals 0 at pi over 2 and at 3 pi over 2. So I apologize about that. We missed a solution. Anyways, we're going to plug it back into the original equation, which is cosine x plus 1 equals sine x. So we'll start with pi. Cosine pi is just going to be 0. Plus 1 equals the sine of pi, which is 0. Oh, wait, no. Cosine pi is negative 1. Sorry. I got to review my unit circle. Okay, so we get negative 1 plus 1 equals 0, which works. So that one is good. Oh, I shouldn't use red, actually. I'll use green. That one is good. So pi works. Now, plugging in the next one is going to be pi over 2. Okay? So we say cosine pi over 2. And then we get 0, because cosine pi over 2 is 0. So we get 1 equals sine pi over 2, which is also 1. So this one also works. But now we have one more, which is 3 pi over 2. So trying that one, we go cosine 3 pi over 2 plus 1 equals sine 3 pi over 2. Cosine 3 pi over 2 is 0. Yep. We get 0 plus 1 equals sine 3 pi over 2, which is actually negative 1. So then we get 1 equals negative 1. That's not true. So that means 3 pi over 2 is not a real solution. We just got that because when we squared both sides, we created solutions that weren't actually there. So those are our solutions. Yeah, it's just going to be pi over 2 and pi. So how we write that, this one, there's no bounds again. So it could be anything. So we say pi over 2, or x equals plus 2 pi k, and pi plus 2 pi k. And remember, the 2 pi is just because the period of cosine. Whoa, that is, again, terrible. The period of cosine is 2 pi. Yeah, so that's the reason. Now the 2 pi is there, and then the k, again, is just some random constant. But we just have to add that because we weren't given like a restrictive boundary for what to do. Okay. So the next example is going to be 2 cosine 3t minus 1 equals 0. Basically, all we're going to do here is add the 1 over. This is where we're going to start, okay? So then we get 2 cosine 3t equals 1. And then we know that cosine 3t, just by dividing the 2, cosine 3t is going to equal 1/2. So where does cosine equal 1/2? Well, on the interval 2 pi. So this one is also another one with an interval. Sorry, I should have mentioned that. So it's from the interval 0 to 2 pi. So that just means we only want solutions that are contained in this interval. So where does cosine, just ignore the 3 for now. Where does cosine equal 1/2? It's in two places on 0 to 2 pi. It is going to be at pi over 3 and 5 pi over 3. Okay, so now we know that cosine pi over 3 and 5 pi over 3 equals 1/2. And what we're going to do is we're going to say 3t equals pi over 3 and 3t equals 5 pi over 3. And then just by dividing the 3 over, we're going to get that our t is going to equal pi over 9 because the 3 comes down and you multiply them together. So t equals pi over 9 and t equals 5 pi over 9. And since we didn't square anything, we don't have to check our solutions on this one. We just know they're right. So we're good to go. So that one ended up being pretty easy. And then I think this is the last example. Oh, it's another pretty easy one as well. Okay, so hold on, I'm going to pause while I look at this example. Okay, so I'm back again. I just had to look at the notes of that example, so I made sure I understand it. Okay, but this example. 3 tan x over 2 plus 3 equals 0. So obviously the first thing we're going to do is subtract the 3 and then divide by this 3. So we're just going to get tan x over 2 equals negative 1. Okay, so looking at the unit circle, tan equals negative 1 in two places, right? At 3 pi over 4 and at 7 pi over 4. But also keep in mind, the period of tan is just pi, right? The other ones are 2 pi, tangent is just pi. So since 7 pi over 4 is greater than the period, we're just going to cross out that solution because it's greater than the period, so it doesn't work. So I'll just put ignore 7 pi over 4 and then parentheses not contained in period. Okay. So we're just saying that. All right, and it's tan x over 2, yeah, as well. So then we just say, wait, I'm in the wrong. Then we just say x over 2 equals 3 pi over 2 plus pi k, because remember the period of tan is pi, so it's just the pi instead of the 2 pi there. But then what we're going to do is we multiply, 3 pi over 4, not 3 pi over 2. And then we multiply both sides by 2 to get the x on its own. And then we're going to get x equals 3 pi over 2 plus 2 pi k. And that's going to be our general solution. Our particular solution is just 3 pi over 4. And again, since we didn't square anything, the solution works. So, yeah, we're good. That's all the examples I have. So, hopefully this video made sense. If it didn't, go find Ms. Williams because I'm sure she would do a better job of explaining it. And, yeah, thank you for watching. Like.